So, gentlemen, good morning once again, and my sincere apology for the small delay. So today is the third day of our training. It's a 10 weeks program that will cover 3 key areas of water reticulation, sewer and stormwater design as module 2, and then road design as module 3. So this is our third day on module 1. The first day we did introduction, we defined the parameters, we set the pace. The second day, we went into the calculation, into the exercises. So today, we're going to do a practical real-life case study, which we actually started last week. But I feel that we should concentrate on that today. Then the last 1 hour we have, we'll introduce ourselves into open source software that one can use to model, basically to model your design. I always tell people that design is something that an engineer must do. But So this is a typical layout. And this is what normally somebody will be given to do a water reticulation design, to do an infrastructure design. The black dot, like I said last week, represent houses, and then those are the roads. So this is just a small case study just for us to grasp the whole concept. So if you look at it, last week we talked about the basic things that you need to do a design. We said the first thing you need a map. You need a map and a topo map, not just a map with the topology of the place, topography of the place. We said the essence is for you to know the highest point and the lowest point, because 90% of water design systems are gravity-based systems. So in this design, you see that the highest point is at somewhere here, and is at 320. And the lowest point is at 250. So if we do 320 minus 250, that will give you 70. So that 70 gives the pressure of the zone. So we say that pressure must not be more than 8 bars. They must limit it to 8 bars. Once it's more than 8 bars, then you have to go into zoning. You have to zone them. So, but in this case, we are having 320 meters above sea level minus 250 meters above sea level. It means we are within one zone. It can comfortably be designed as a one-zone system, where the pressure in the system will be between the highest point and lowest point cannot be more than 7 bars. Okay, because 70 is equivalent of 7 bars. So we also said that the calculation sheet looks like this. This is how the calculation sheet will always look like. You know, we will do other type of design. We have other things in mind. But in this case, which is a water reticulation design, this is how your calculation sheet will look like. I'm trying to rotate it. Okay. So this is what it looks like. The first point, it shows the sections. Here is point Z. But this is the point of storage tank. First point, point 2, point 3. When a surveyor gives you a topo map, it will give you in terms of points. That's the normal thing. There's a point, XY coordinates, point 1, point 2. So this is the ST means storage tank. This is point 1, this is point 2. Then when you now read it as ST1, this is now the distance between the storage tank and point 1. The second one is the distance between the point 1 and point 2, which is 60 meters. The distance between point 1 and point 4 is 120 meters. So as I'm looking at this thing, I want you to also bring out this map and be seeing it. And then also the simplified one. So this is the simplified map here. Okay, so it is in sections. Section 1, storage tank to section 1, section 1 to section 2, section 2 to section 3, section 1 to section 4, section 4 to section 8, in that order. So it's going to be in that order. Okay, it's going to be in that order. So your job now, like I said last week too, you need 4 parameters. Okay, and those 4 parameters are, you need the length, you need the quantity of flow or the demand the demand of the water at every node. Then you need the diameter, and then you need the elevation. So I classify them as 2 parameters, 2 pipe parameters and 2 node parameters. When we say pipe parameters, we are talking about the length of the pipe must be known and the diameter of the pipe must be known. when we talk about the node parameters, we are saying that the elevation of each node must be known, and the what again? The quantity in each node must be known. So pipe, the diameter and length, then the elevation, the point, you need the elevation of the point, which is a function of pressure. That's the idea, to be able to determine the pressure at that point. And then you also need what is the water demand at that point. For instance, this is node 13. Here is node 13. Okay, so node 13, it means node 13 will take care of all the houses within this length of pipe. So it means at this node 13, I must know the pressure, the elevation, and I must know the demand. Then along this pipe, which is pipe 6 to 13, or section 6 to 13, I must be able to know the total length of the pipe, because that's a function of friction, roughness, losses. Okay, yes. And then I also have to know the diameter, which is actually the key parameter you're looking for in water recirculation design. It is to design the pipes. The pipe is your end product, your final output. The diameter of the pipe is your final output, because that's what you're going to procure in the market. If the pipe diameter is not adequate, the water will not flow. Or some people will have water, those are the upper stream, will only have water. Those are the lower stream, downstream will not get water. That's the point. That's the essence of sizing. So the whole thing about hydraulics of infrastructure for water is about pipe sizing. But then to size that pipe, you need to know the quantity. What quantity do you need at every node? Because the water is flowing from ST to all the nodes. So if you use the wrong pipe, you only see that people up to the point of 3 or 4 only have water. Those are 6 and 13 will not have water. Why? Because the diameter of the pipe is inadequate. So, but to get the diameter of the pipe, you need the length of the pipe. Okay, you need the slope of the ground. Okay, and then you need the quantity of water to be transmitted. So with those two parameters, you now go to your nomograph, which I showed us last week. And I said last week, there are many of such charts in the market. I mean, this one was developed by the University of Stuttgart. If you go to MIT, they'll have their chart. I mean, we are engineers. We make use of charts. And then last week also, we talked about nominal value. Remember? Nominal value. A situation whereby if once I get the Q, the quantity of flow, I'll read up in my chart. I read up from my table, sorry. And I'll know exactly the type of pipe that I need. But here, we said, if you want to be more precise, you want to be more accurate, then you might consider using this chart, which means the horizontal is the flow and the vertical is the slope. So with the slope of the ground and the flow required, I can easily get my pipe size, which is now the elevation. So later on, I'll still send us a video. You know, some of the things we are doing is we have a lot to show in this training, but some of them will come in form of videos that will just give you watch, that will deepen your knowledge of any particular area where you are not too knowledgeable about. So if I now get my Q here, I will now come here and plot it against the slope of the ground, and then I will be able to get my pipe size. Okay, and we said last week that if we get a pipe size in between two pipes, you use the bigger pipe size for safety's sake. Just like we do in engineering, you go for the worst case scenario. It is always worst case scenario. Okay, you design against failure, and design against failure means you move in the right of safety factors, in the path of safety. Okay, so let us quickly do this. I want you to open the one we've done last week, ABC design, ABC estate design. Just open it, it's a Microsoft Word. So in this ABC design, let me just test this one is just to test our knowledge. Say in ABC, say we are talking about 3-bedroom houses, right? And we said each house has 10 inhabitants. And we said there are 30 streets per street. And then there are 50 streets or roads in the estates. Now, this is a sample question just to test our knowledge, right? He says, what is the water demand per house? So for a 3-bedroom house with 10 inhabitants, what is the water demand per house? And then you also say, what is the water demand and pipe size per street? Why didn't I ask for the pipe size per house? Because that is nominal design, 1-inch pipe or whatever. Three-quarter pipe, you know, that one is 40 mm pipe, 50 mm pipe. You know, 20 mm pipe, 25 mm pipe will do that. So it's like a nominal design. But when it comes to streets that has 30 houses, then probably the pipe size need to be kind of appreciable. So we need to design it. Then the next question says, what is the water demand and pipe size for the pipe of the estate, main pipe? So there are 3 layers of question here. Number one is that this estate is made up of 3-bedroom houses. And in each street of the estate, there are 30 houses. And then there are 50 of such streets in the estate. So already, if I ask you to calculate the population equivalent, it will be 50 times 30 times 10. And that will give you 15,000, right? So this is more like saying we're designing for a 15,000 population equivalent or 15,000 per capita. Okay, that's just what it means. So let us solve this problem before we go to the ABC design. So, but then, like you said, we assume 10 people to be in each flat, in each house. This is already existing place. If it is not existing, then we use the land use of the place. Land use will tell you that we expect 300 persons per hectare. We expect 600 persons per hectare. We expect 1,000 persons per hectare. That's how you use land use. If it's a virgin land, a place that there's no existing infrastructure, there's no existing building, then you need to ask question, what is our proposed prototype? Is it 2-story building? Is it 4-story building? What is the density, population density, which is just a way of saying what is the land use. If there's no land use in this area, you make assumption, reasonable assumptions. Okay, so here we are assuming that the slope of the place, the average slope of the place is 0.5. In real sense, you have to measure it. Slope is the difference between the vertical over the horizontal. So if a surveyor gives me 2 points, if a surveyor gives me 2 points, point A and point B, with elevation difference of 2, and the distance between those 2 places is 100, it means the elevation is 0.02. I mean, we can't start at this level, we can't start teaching people about how to get slope. And then we said we're using a peak factor of 2. Remember what we said 2 weekends ago? You need a safety factor, an assumed safety factor. And I told us that Abuja was designed with a safety factor of 2.3. I've said that before. Okay, 2.3, they use 100. But knowing that Abuja is going to be a very fast-growing city, they anticipated that there's going to be a population explosion. They factor in they use a safety factor of 2.3. What that means is that, assuming you design Abuja for 1 million people, even if you have 2.3 million people, the water will still take them. That's the implication. That's just what safety factor means. It means we are designing Abuja for 1 million people. But if peradventure, all things being equal, by the way, and the population grows to 2.3 million people, that is when we start designing for a new phase. Or that is when we start increasing the capacity of pipe, or introducing some segments, or introducing new zones or new phases, or we begin to change our water tanks, or we begin to do some other upscaling or upgrading. The idea, gentlemen, is that when you lay these pipes on the ground and you make a mistake, retrieving them is a disaster. I have seen where people spend 200 million naira and the consultant did a bad job, and everything is just go down the drain. So that is why, as an engineer, you must not play with your safety factor. Not to talk of the other errors, other contingencies that are inherent in safety factor. Safety factor is where you hide your errors or your uncertainties. You know, it's a form of a sensitivity analysis factor. Okay. Now, we said the specific water demand per person, per capita per day is 100. So let us answer those questions now. So number one, let's do some conversion, some unit conversion. We said that 1 day is 60 by 60 by 24. So 1 day represents 86400 seconds. And we also say that one meter cube is equivalent of 1,000 liters. So the question is, what is the Q and what is the diameter? Once you get the Q, you get the diameter, your design is done. What you need to do is to go back to the design, draw lines, and then indicate pipe sizes, length of pipe, and all those things. Just do the detailing there. That is what it means. It's as simple as ABC. The detailing is not AutoCAD. Just draw a line. And then for each pipe segment, you now indicate either down by the side or top the value of your parameter. I will show us some samples here. I will show us. Okay. So let's go. So let us remember this age-long formula that we always know, which says that Q is equal to AV or CIA, where C is it depends on what you are doing. Now, if you are talking about volume, it is surface area times the volume will give you the discharge. Now, discharge can be used interchangeably. You can use discharge, you can use demand, you can use flow, you can use any word. They are all the same terminology. So if you multiply the surface area of a pipe times the volume, it will give you times the velocity, sorry, it will give you the Q, which is meter cube per seconds or meter cube per hour, okay? Or whatever you need to use, or liters. Then, if it is in rain, when we'll be doing sewer and stormwater next 2 weeks, it will not be CIA, where C is the coefficient of flow or coefficient of runoff. I will be the rainfall intensity, and A will be the land area. So what this red thing is telling us that engineering is the same. Once you understand the concept, the back-end concept of a formula, it becomes the same. This AV can also be written as small q times A. So the flow rate, the volume of water per seconds is the product of the flow rate multiplied by the surface area. That's all what it means. So for this 3-bedroom, we say 10 capita per 10 persons per room. And we say each person will consume 100 liters per capita. And then the safety factor is 2. So automatically, for this 10 persons apartment, what they need is 2,000 liters per day. Or since 1,000 liters is meter cube, it means they need average of 2 meter cube per day, after factoring in a safety factor of 2.2. So 2,000 liters is what a family of 10 needs, okay, per day. However, we said that in designing your pipe network, we deal in seconds. We deal in second hours. That's the word. While if we're sizing tank, reservoir, we size it based on per day. What is the capacity per day? But when you're sizing pipe, you don't say per day, you don't say per second or per hour. But all of us know that in modeling, you discretize to the smallest denominator. So in this case, we now divide 2,000 by A600 to convert this day to seconds. So if you do that conversion, you're going to get 0.023 liters per day. Okay, so now this is now the flow we need per room per house. So the answer is 0.023. The second question says that there are 3 houses in one street. So what's the quantity required per street? And what is the equivalent pipe that should be laid on that street? Okay. So now, number B. So we said, since there are 30 houses and each house has 10, it simply means we are designing for 300 persons, 30 times 10. And since one person requires 100, and the safety factor we are using is 2, we just multiply everything together. Our answer will give us, our answer is now giving us 60,000 liters per day. If you do the conversion, you are going to get 0.69 liters per second. So this 0.69 liters per second, we now go to our pipe, our chart, to size the pipe. Let me just give you a rule of thumb. Any value that is less than 1 liter per second, use 1 liter per second. That is what the rule says. So it means in your pipe network, there is a minimum benchmark. There is a nominal pipe size. In SEWA design, the nominal pipe size is 150 mm, 6 inches pipe. You are not allowed to use anything less than 6 inch pipe for your SEWA design. But in pipe design, you need to use the value for 1 liter. And gentlemen, that's about 65 mm. I don't need to tell you. So it depends on this velocity, this slope. So that's why last week I gave a general advice that the minimum pipe size in your network, in your infrastructure work, should be 75 mm, 3 inches pipe. Don't use 2 inches pipe. You can use 2 inches pipe within the house, but for outside the house, the ones you lay on the road, on the street, let your minimal pipe design be 3 inches. Then of course you can increase as you go towards the source. So here now, you now read the graph. So if I read the graph now, in this case, I'm using the graph. I'll read 1. In 1, I have a slope of 0.5. So if the slope is 0.5, it means that is 5 per mil. I've explained how this chart works. This is per 1,000. So I'll read my chart against 5. So I'll go for 5. So if I go for 5, you can see that the value is giving me between 50 and 65. You see where people made that mistake. I've seen a lot of designers, they'll use 50 mm. But you can see that the pipe size for 1 cubic meter, 1 liter per second, 1 liter per second, servicing 300 population equivalent, requires a pipe size of 65. So this is 5. Then if I go diagonally down, the velocity at that point will be 0.4. Why are we interested in the velocity? We say that the velocity is for check, because the code, the standard says your velocity must not be less than 0.3, and it must not be more than 3. If it is more than 3 meters per second, it will lead to supercritical flow. If it is less than 0.3, it will lead to also other form of problems. Okay, so the pipe size to be used for the design will be 0.69. And that is it. Okay. Okay, so I say choose the bigger of the two or the most available in the market. If you go to Nigerian market, you won't see 65, except you're going to custom import those pipes. Okay, so number C says, what will be the main pipe? Well, we've said that we need a 65 mm pipe to design for the streets. Okay, now the next question now is, there are 50 streets in the estate. What is the size of the biggest pipe? In other words, that pipe that is coming directly from the water source, whether they're using groundwater or water from the tank, or the pipe coming from the tank, the main tank, assuming they're using one tank. So that is what the question says. The question now says, what is the size of that particular pipe? Okay, so the same thing happens. Very simple. You just multiply 50 times 30 times 10. That will give you 15,000. That means there are 15,000 people in that estate living in 30 streets, living in 10 persons per house, 30 streets, no, 30 houses in the street, and 50 streets in all. So here, let's go. So we do the same design, the same thing we did, 15,000 times 100 times 2. That will give us this. Then it gives us 3,000 liters per day. If you divide it, you get 34.7 liters per day. Let me also tell us one thing we need to know here. If I'm to size my tank nominally, right? Nominally, because there's a formula for sizing tank. This thing can also give me an idea of the kind of storage I will provide. However, we talked about design consumption. If you want to optimize it, then you need to understand the consumption pattern. The consumption pattern will help you know that when to pump, when not to pump. We discussed it last week. There's a period of time you pump water and you maximize your tank size. And then it also depends on how many times you want to pump in a day. I don't see people pumping once a day. In some of the treatment plants they have in Abuja, they pump every 1 hour, even though I know that is absolutely wrong because that would be so much consuming a lot of energy. But the problem is that the tanks they provided, the 6 tanks that are operating in Abuja as we speak, are very small. There are supposed to be 10 tanks servicing only phase 1 of Abuja. So far, FCD have built only 5. And those 5 were built maybe for 4 hours, 6 hourly pumping. But because of population equivalent explosion that has taken place, they keep pumping almost like every hour they are pumping. They pump, they shut down, I don't know how they do it anyway. Or maybe 2 hourly pumping. Maybe I got information. Okay, so this 10,000 naira also tells you this is the volume of water you need to provide. But if I'm to pump, I have 12 hourly. I'll divide this factor by 2. That becomes my tank size. If I'm pumping water, like 6 hourly, I'll divide this value by 6. That becomes the size of tank I'll need to provide. It means every 6 hours that tank will be empty. Okay, so let's go to the pipe sizing for this for the main pipes now. So we read 34 against 5% like we did for, and this will give us a pipe size between 200 and 250. Okay, good. Then if you check the chart very well, you'll find out that 30 liters, if we are talking about 30 liters, it is for 200. If you're talking about 50 liters, it's for 250. So this is where engineer makes a decision. If you go to your chart, for instance, this is 34. 34 against 5. You see, it's somewhere between 200 and 250. The question now is that which one do you take? Since 200 is 8 inches pipe, 250 is 10 inches pipe. But now, I now check 30. 30 is giving me 200. And if I have to use 50, 50 is equivalent of, if I'm to use 250, 250 can take as much as 50 liters per second. The question now is, what do I choose? This is where you as the engineer need to make the decision. For me, I said it's better we choose 200. Even though we said choose the bigger of the two, but the bigger is too much. The value I got is closer to 200 more than it's closer to 250. A bad designer will choose 250, but me, I will choose 200, having in mind that I've already factored in a lot of safety factors of using 2. Some people can use 1.5 as a safety factor, but I've used 2. I have used 2, so that is enough. So in this case, gentlemen, we'll break the rule and use 200 because it is not economical to use 250, and it's too high, it's too much. So it means for this estate that has 15,000 population capacity, I will need a pipe size of about 8 inches or 200 mm to bring in water. Remember, there are 50 streets. So the question now depends on the alignment of the streets. Maybe there are 4 sections. If there are 4 sections, it means probably after the 200 comes in, it will branch off into 150 to service 10 streets. Then as soon as it's going down to service maybe 5 streets, another 5 downstream 5 streets, it will break into 100 mm. Then finally, it will end at 65 mm, which will be the least pipe I will need in this place. So for the ABC design, okay, we're going to solve it now by understanding the 4 parameters I talked about. The node parameters, do we have the elevation? Do we have the demand? Okay, so for you to get the pipe size, you need the discharge. So in other words, there will be 2 known and 2 unknown. If I send a surveyor to the site to go and map an the survey information will give me 2 things. It will give me the length of the pipe. I can read it out from AutoCAD. Then it will give me the elevation of every node because there will be contour lines. So I can read off the elevation of every node. Okay. The second one is the pipe parameters, which is the length of the pipe and the diameter of each pipe. What is the length of each pipe and what is the diameter of each pipe? So, like we said, we all know this. Q equal to AV, and it's going to be A1 V1 plus V2 V2. So it means the total final length of the final diameter of pipe will be a function of the summation of other downstream pipes. I mean, this is a simple thing. So here, for this exercise, this design here that we're going to do now, okay, we are assuming that each of these houses is a 4-bedroom duplex. We are assuming it's a 4-bedroom duplex. These are the state uniform design. So it's going to be a 4-bedroom duplexes. And we said that each duplex will have 20 people dwelling inside. Yes, somebody can argue that this is too much. Yes, you can reduce it to 15, you can even reduce it to 10. But remember what we said last week. You must design for worst case scenario. Your final population projection must take into account the lifespan of your proposed water system. If I want the lifespan to be 50 years, in other words, in 50 years' time, there won't be any new design. Then I need to use the population at 50, as well as development and other factors that we have discussed that I need to put into consideration at 50. Now, for this one again, we are retaining the fact that the water demand per person still remains 100 liters per capita per day. Okay, then we say we will also use a peak factor of 2.0. So in other words, let us establish the water demand per house. So here it says the water demand per house will now be 20 times 100 times 2, which will give us 0.046 liters per second. That is the amount of water that has to be flowing in each house. Okay, so let us start with note 13. If you are designing your water reticulation system, it is ideal to start at the lowest end. If you want to do a discretized design, you want to get the values per one. I have seen many designs where people just design the main, and I say it's not wrong. Sometimes you don't need to start counting houses. No, like I can count the whole number of houses in this estate and then give them one pipe size and say this is the main pipe. Then when the person goes to the site, he can start to discretize. But in this case, let us, for the purpose of learning, let us do it one by one so that we will all understand it properly. So all houses along section 6 to 13. Section 6 to 13. This is 13. This is 6. 6, 13. Section 6 to 13. So all the houses along section 6 to 13. So all the houses along section 6 to 13, we'll count it. What did you get? So in this case, we got 23 houses. So we simply multiply the water demand per house by 23. So that will give us 1.065 liters per second. And knowing that the slope is 0.5, gentlemen, from what I said, you don't need to go to the chart even. The answer is 65 because this is 1. So I just assume this to be 1. And we say anything that's less than 1 maintains 65. So what it simply means, anywhere I go now, I see 1 liter per second. I don't need to cut my head. The pipe size is 65. That's what it means. At some point, you also find that you can establish those kind of benchmarks. Once the pipe is below 2, the pipe size will be this because you've done it one, you don't need to repeat it again. Then I check the velocity. The velocity is within acceptable limits. So this pipe has been done. So I move to note 6. So in note 6, there are houses along here and there's houses downstream. So note 6 is the one supplying note 13. So whatever value note 6 we have, it will first of all consider that it will release some quantity of water to those people living between 6 and 13. Yes, so note 6 here is now all the houses lying between 7 and 6. When I get the value, I will now add it to the value I already got for 13 because note 6 is upstream. So in this case, node C says there are all eight houses, 4 are undeveloped. So I'll simply say 8 multiplied by this. The answer is 0.37. But that is not the demand at node 6. That is only the sink. I call it sink. That is only the sink at node 6. We'll now add it to the downstream value of node 6. And the downstream value of node 6 is what we just did in node 13. And that is 1.065. So add it plus 37. That will give us 1.44. I don't expect the pipe size to change. So the pipe size remains 65. If you want to go and check it, anything between 1.11 and 1.44 is still pipe 65 will still take it. In fact, probably 565 will take up to 1.6 or so. So you can see that pipe sizing, the capacity of a pipe is not static, it's range. That's why last week I also told us that your pipe should flow between 70 and 90% full for a pressured pipe, for a pipe under pressure. Okay, or you call it a closed pipe. It must not flow 100%. It must give buffer, or would I say overboard? Is it overboard? That's the word again, freeboard. Okay. So go to house 10. So this is house 10. House 10 is at the edge. So house 10 does not have downstream. So it's house 10 will just be 10 houses. I count the number of houses connected to house 10. Okay. The number of houses connected to house 10 is about 10 houses. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 houses are connected. So in these 10 houses that are connected, simply say it's house 10. Okay, house 11, sorry. It's house 11. Node 11. So node 11 has 10 houses connected to it. So that will give 0.46. Because it's still less than 1, we just give it 65 mm pipe. We go to node 7. Okay. Node 7 will say what is the base demand? Okay. Then multiply, add it up to the flow. So this is node 7. Let me demonstrate it here. So this is node 7 here. So if you look at node 7 has 2 downstream. It has 2 nodes downstream of it, which is node 11 plus node 6. So when I'm calculating for node 7, I will first of all calculate the houses between 8 and 7. That becomes the sink, or its own base demand. That's what we call it, its own base demand. Then I'll now add it to the secondary demand, which is node 11 and node 6. Because when node 7 service the houses along these places, it will still service node 11 and service node 6 because water is flowing upstream, because he is upstream of the other 2 nodes. This thing I'm trying to explain is the crux of the matter. This is where engineers failed it, and this is the real thing. This is the real take home. If you can understand this section and understand this very well, you don't have any problem. Like I said, the EPANET thing is just for modeling. It's just for you to show expertise, okay, and show more. Give it a professional outlook, professional touch. Give your design a professional touch, because EPANET will give you the values, give you the readings and everything. Okay. So that's it. So here, there are 6 houses connected to 7 directly. So we'll say 6 times the demand for 1 house. That will give me 0.28. Therefore, the total demand will now be its own base demand plus the demand at node 6, then plus the demand at node 11. And that will give you 2.18. In this case, it has gone beyond 65. So I'll go to my chart and read it. I'll go to my chart. This is 2. 2 against 5 per min, somewhere here, is now about 80. So the value now is 80 mm, which, if this is Nigeria, I'll use 75 mm, because that is what we have in the market. We have 75 mm, 3 inches. We don't have 80 mm. Maybe other countries might have it, but 80 mm is the actual value. It's not you that we use. Remember what we said, depending on market availability, or convenience, and whatever, or other factors. So I'll use 80 mm. So let's go to node 12. So this is node 12. Node 12 it does not have downstream. So I'll just calculate houses between 9 and 12. So if I calculate the houses between 9 and 12, I will get 8 houses. So 8 multiplied by the value of 1, that will give me 0.37. So I'll just use nominal pipe. Node 10, I think those 10 has the same, shares the same fate as node 12. Look at node 10. So all the houses between 9 and 10, and there are about 10 of them. Okay, I'll just multiply 10 times that value to still remain nominal pipe. So you can see that the end pipes are just effective because there are no downstream houses. So, but now, if you come to node 9, node 9 will now be node 10 plus node 12. And maybe if there's anyone between 8 and 9, but there's none. So node 9 simply means node 10 plus node 12. So here you see node 9 is equal to node 10 plus node 12, and that will give you 0.83. 0.83, it means the same nominal size. Node 8 now will be the value of node 7 plus value of node 9. Why is it so? Because those are the tributaries, sort of. See 8 now. So 8 will be the value of 7 and the value of 8. So, and if I go here now, value of 7 and value of 8, that will give me about 3. And luckily, 80 mm is still good, can still carry it from the chart. We'll go to node 5. How is node 5? Node 5 is standalone. So I just count the number of houses here and do the calculation. So 15 times the value for 1 will give you 0.7. The value, the nominal pipe size remain 65. Next, we move to node 3. Node 3 is also standalone. Look at node 3. So we'll calculate all the houses along here. Don't mind these dotted lines. I'll explain what it is. These dotted lines simply means if I'm doing loop system, I'll just loop it. So if I'm looping it, so that if there is servicing of water here at node 4, water can flow from node 2 to node 3. That's simply what it is. I'll still explain further. So here we're talking about node 3. So node 3 is very straightforward. Then we now go to node 4. Node 4 is more complicated. Node 4 will now be the value of 3 plus 5 plus 8. Very simple. 3 plus 5 plus 8. So let's go. So node 4 becomes node 3 plus node 5 plus node 8. No? Yeah. Node 3, node 5, node 8. And then houses that are connected to him. That's true. And if you check this thing, you see that there are 10 houses. See, node 4 is here. There are 5 existing houses and there are 5 undeveloped plots. So like we said, you have to add them. So it becomes 10 houses, total of 10 houses connected to node 4. Therefore, that will be 0.74 plus 0.69 plus 3.01 plus 0.46, which is node 3 plus node 5 plus node 8 plus this. So it will give me 5.91. And when you go to the chart and read it, it will give you 100 mm. So if you go to 5 here, and you go up, up to 5%, it will give you 100 mm pipe of what we call 4 inches pipe. Then we go to node 2. Node 2 has these houses. So node 1 becomes node 2 plus node 4. That becomes 0.24 plus 4.9 we got before, and that will give you 5.1. And the pipe size becomes 125 mm, and the velocity is still very, very good. So it means the biggest pipe in this network will be a 5 inches pipe or 125 mm, servicing maybe about 100 houses. Okay, if you count the whole number of houses there, it's about 100, and count that each house is 20%. So that was about almost like 20 times that 2,000. So this is designed for a 2,000 capacity. So as an engineer, and I ask me if I check and I see that that place I'm designing has 2,000 people. I can leverage on this and say, okay, for interview. I'll simply come here and I'll fill in the queue, the discharge queue. So the queue here, 1 to 2. The queue at point 1 is 1, 2 is what did we get again? 5 point something. The queue at 1 to 2, I think we got about 0 point something. Then queue at 1 to 4, we got about 4 point something. In that order, I'll fill here. Then the queue, the diameter of the pipe, we got about 125, 100, 65, 65, 65, 75, and in that order. I'll just fill it here. But practically, I'll use 2 pipe sizes, 100 mm and 75 mm. It will do the work. Or 3, 125, 100, and 75. I don't need to go too deep. Discrete. Okay, so that is the end of the design. And I hope there's no question. So the next thing we're going to do now is we're going to move to I have a lot of recorded videos on the software application. But let me give us a head up by we doing one exercise today. So I don't know whether we are ready. I don't know. Let us go to online and download go to Google. You type epa.gov, but the program is, I don't know how many of us have downloaded it. epa.gov. Enter. Or you just type EPANET online to take you to the place. Here I can come here and type EPANET. When I go to the EPA website, I type EPANET. So EPANET, I will now click on the first one. And I will download it. Please, I want to say, how many of us have downloaded it? You come here, you see the latest one, self-extracting installation program. You click on it. It will download the program. You save it somewhere. Please download it as I downloaded it. Go to Google, go to EPA website. But if I've downloaded it, just say yes. Then I go here, I click on this, and then I run it. That's all. It take you just a few minutes. You just click yes, 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 yes. It's a very simple software. EPANET, I have it already. Are you there?